comes out to be about, can anybody guess? Anybody know the radius of a hydrogen atom in a 1s orbital?
1 angstrom.
Okay, you know the diameter is about an angstrom, right? So what's the radius?
Half an angstrom.
Half an angstrom. So it's going to be like 0.5 times 10 to the minus 10 meters, all right, times n squared, which very often is written as R0 times n squared, or R1, or I think it's A0, where this is Bohr radii.
A0.
What's that?
Is that A0?
Yeah, A0, Bohr radius.
So we also do show what?
So you're Bohr. You have these classical results, and you have this new quantum mechanical idea. By somehow solving for R in terms of n, you can get it to look like this. And when you solve for R in terms of n, what you found is this result. That here's my new prediction. I now predict, with this one approximation, this one new idea, that the Bohr radius is about half an angstrom, for n equals 1. And indeed, that's about the size of an atom, the radius of an atom. All right? The other thing is you can solve for E total n. All right? And when you make all these substitutions and plug them in, by all means, you can go and use your modern book and look and get help and things like that. But what it comes out to be is minus 13.6 eV over n squared, where an EV is equal to 1.6 times 10 to the minus 19 joules. So in EV, it's called an electron volt. And an electron volt is the amount of energy, 1.6 times 10 to the minus 19 joules. Here's the scoop. An electron volt, if you had a potential difference, if you had 1 volt potential difference, plus, minus, right? And 1 volt is a potential energy. Remember, a voltage is a joule per coulomb. Okay, so a volt is a volt equals a joule per coulomb. The energy of a particle in a potential field is equal to Q, the charge, times the voltage. So in this case, if I put an electron right here, what would be the energy the electron feels in this potential?
It's the charge of the electron times the
It would be 1.6 times 10 to the minus 19 coulombs times 1 volt, and a volt is a joule per coulomb. Coulombs cancel. It comes out to be 1.6 times 10 to the minus 19 joules. All right, so an EV is the amount of energy that an electron feels in a 1 volt potential. That's it. Or you could also say it's the kinetic energy of an electron that was just accelerated through 1 volt potential. Because if I put the electron here, it's going to accelerate this way. Yep.
Wait, 1.6 times 10 to the negative, what is that?
Minus 19.
Okay, so that's the energy it feels when 1 volt.
So if I have a 1 volt, it's always hard for me to introduce this because I think people forget that and don't quite get the concept of a volt. A volt is not a potential energy. A volt is a potential energy per unit charge. So to find out how much energy is there, you've got to multiply how much charge you have times the potential difference. All right, so a volt is a joule per coulomb. So if I have a 1 volt electric, and the names get worse, an electrical potential is not the same as electrical potential energy. And electrical potential is an energy for you to charge. That's why, it is hard. I mean, the letters we use, here we're using the volt, but pretty soon, but we've also already used it as a velocity, right? Mm-hmm. And when we write the Schrodinger's equation, it's going to mean the potential energy. Here it's the electrical potential, which isn't the potential energy. Okay, so it's, for example, I don't want to go too far into it.
It's like the gravitational field of Earth is 9.8 meters per second, but it's going to be different depending on what mass that I put in that field.
The potential. Yeah. Here's what I do: is I say I draw the following analogy that some people like and some people don't like. The gravitational potential energy is mgh to some approximation, right? mgh. I could define a gravitational potential as mg. I mean, it's gh. And gh would be like the gravitational potential, which would be an energy per unit mass.
You put something at a certain height, on a certain
right. And so it essentially tells you how high the hill is.
Like about the mass.
And then to put in how much energy you have, you got to multiply that gravitational potential by m. So then you have the gravitational potential energy. Right? It's a nice connection to make, and I think some of you guys have more familiarity with it if you're taking digital, and we'll talk about this in a little more detail. Okay, but the long and short of it, look, we can clear this stuff up, is that an EV is a chunk of energy. Alright? And so what happens is the following. Up here, you're going to get the total energy in terms of all these constants. You've got to fill in all these constants, get the energy probably in terms of joules, and then once you get the energy in terms of joules, convert it to EV. So this is for Thursday. You've got to do this. All right, you got this. Okay? So, first of all, here were the problems that accelerating charge radiate. So the way out of that is Bohr said, look, I'm going to assume that these orbits, these fixed radius, these quantized orbits don't radiate. So these are the orbits that do not radiate. When an electron has this quantized orbital angular momentum, it does not radiate.
So where does the photon come from?
No one knows. that's another
fun.
All right. Finally finished his PhD at MIT, got all done, and was feeling all excited.
His PhD was Princeton, not MIT.
Oh, that's right. He undergrad at MIT. So was this his undergrad?
This was when he finished his PhD at Princeton.
Got all done his PhD at Princeton, and Wheeler was his advisor, John Wheeler. He was incredible. And when he got all done, his dad came up to him and said, "Oh, you just finished your PhD from Princeton, and I understand about this whole model and everything, that it radiates and everything, but where does the photon come from?" And then Parker goes, "I don't know." All right, so just finished PhD, couldn't answer the first question. Okay, so the first thing was, Bohr said these are the orbits that don't radiate. All right, that's it. Didn't have an explanation, he said that's just the way it is. All right, and the total energy is 13.6 eV over n squared. All right, so now let's check with an experiment. All right, so if you put an electron, if you take hydrogen in an electric field, here's plus and then here's minus. So there's my electron. All right, and you put it in a potential field. Here's plus, 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 minus, minus, minus. Then what happens is the electron gets pulled a little bit to the plus side, and the nucleus gets pulled to the minus side. And at some point, if you give enough potential, you can pull those two apart, and that's called ionization. Right? And what it was known experimentally is the ionization energy of hydrogen was minus 13.6 eV. So right away, Bohr's result, he just solved something that nobody knew before. How to figure out the ionization energy of hydrogen.
Is that minus 13.6 or is
Well, it
that...
depends. I say minus meaning I've got to put minus into it. So in other words, I say minus meaning that somebody had to add 13.6 eV into it. All right?
To get there. So
To get there, yeah. The way the atom is set up, it's set up as a bound system. So when you're in a hydrogen atom, if you have zero energy, you're free, right? But since you're bound, that means you're minus 13.6 below zero energy. But if I'm minus 13.6 EV, how much energy does it take me to get up to zero EV? If I start out as minus 13.6, I got to apply plus 13.6 EV. All right, so all the energies of electrons around atoms are negative because they're all bound. So a free electron with no velocity would be zero energy.
Also, in a hydrogen atom, that's the charge of an electron because it's bound.
Not the charge, its energy is negative because it's bound. Yeah. And so, for example, let's take a hydrogen. So it goes like this. Here's energy, E total. All right, and here's minus 13.6 eV. That's like a 1s. All right, so the energy is minus 13.6 eV, so it's down here. So it takes 13.6 eV to energize it up to 0 eV, to free it, to ionize it. But let's say I'm at say I'm a 4p. I'm a 4p electron. What's the energy of a 4p electron according to the Bohr model?
It's more than, or it's between minus 13.6 and 0.
So ballpark though. 13.6 divided by what?
4.
So it's about an EV, right?
About an EV, yeah.
A negative EV. So in other words, it's minus here, minus 1 EV. All right, how much energy do I need to ionize that 4p electron? 1 EV. Just 1 EV. Okay. But further, this is taking a little bit longer than I anticipated, because I'm talking more as usual. All right. But further, what happened is this. This is the further implication of Bohr's model. Say you had this. Here's the positive nucleus. And let's say my electron was right here in an n=2 shell. All right? And here's an n=1 shell. Or let's just say this is n initial, and this is n final. Okay, so what conservation of energy says? E that you start with has to equal E that you end up with. All right, so if I start with energy of n initial equals energy of n final. Well, what else do we know that what was the other postulate of Bohr? That when an electron above an atom makes this transition, what happens? So it doesn't radiate here, doesn't radiate here. Radiates when it transitions. So, here I am, so the picture kind of looks like this. Here's my start. The finish is that I have a positive, and then the electron in the n=, final shell plus a photon. Okay, so that was Bohr's suggestion. Do you see that? You start with the electron in an excited state, then you end up, the electron has gone from this excited state, n initial, and it's kind of transitioned down to n=, final. But Bohr said that's when you make radiation.